Good afternoon, everyone. Thank you for joining us in this webinar on the interesting topic of neuromorphic artificial intelligence, a new era for robotics. This event is brought to you by the NTU Institute of Advanced Studies, the Graduate Students Clubs of the School of Electrical and Electronic Engineering, the School of Mechanical and Aerospace Engineering, as well as the School of Materials Science and Engineering. I am Shantanu from the School of Electrical and Electronic Engineering, and I will be your host for this Discovery Science seminar. During the webinar, please use the Q&A feature at the bottom of the Zoom screen to post your questions. We will have a Q&A session after the presentation where these will be answered. Now, let me introduce our distinguished speaker, Associate Professor Arindam Basu. Professor Arindam Basu received the B.Tech and M.Tech degrees in Electronics and Electrical Communication Engineering from the Indian Institute of Technology, Kharagpur in 2005, the MS degree in Mathematics and PhD degree in Electrical Engineering from the Georgia Institute of Technology, Atlanta in 2009 and 2010 respectively. Dr. Basu received the Prime Minister of India Gold Medal in 2005 from IIT Kharagpur. He joined Nanyang Technological University in June 2010 and is currently an associate professor. He is the associate editor of several journals and serves on several technical committees within the IEEE. His research has won several awards, including the MIT TR35 Asia Pacific in 2012 and IEEE CAS Distinguished Lecturer for 2016 and 17 period. His research interests include brain-machine interfaces, bio-inspired neuromorphic circuits, and non-linear dynamics in neural systems. This year, I had the privilege of being taught by Professor Basu, and I wish that he was my professor for this subject during my undergraduate as well. Without further ado, let's welcome Associate Professor Basu.
Thank you very much, Shantanu, for the very kind introduction. And thank you all for attending today's talk. I have to thank all the graduate committees for inviting me for this talk, and I hope it's interesting. So since you can imagine, this talk is a little bit interdisciplinary, and there's also graduate students from many different departments, I'll try to keep the talk a bit less deep on the technical part, but try to give you more of a flavor of this kind of research. Okay, so let's continue. Firstly, I'll show a picture about the people who did all the work. So these are this is a snapshot of a group dinner at sometime a few years back. So these folks did all the work that I'm going to present today. And in my lab at NTU, we broadly work at the intersection of brain and electronics. And you see the arrow goes both ways. So we make electronics that are inspired by the brain, which is more like the neuromorphic part. And we also make electronics that are implanted inside the brain to give us more understanding about how the brain works. So in general, we work on neuro-inspired or neuromorphic circuits, algorithms, and systems. And we apply them to several applications, ranging from brain-machine interfaces to Internet of Things, machine learning, and some emerging areas of hardware security. Okay, so now coming to today's talk, this is kind of a brief outline, and I would like to start off first by talking about, what does this term neuromorphic really mean? So the term neuromorphic was coined by Professor Carver Mead at Caltech in the 90s, and Carver happens to be my academic grandfather. So I am kind of obliged to show this slide. So what Carver postulated was, if you look at the operations in the brain, what we are very good at, humans, very good at finding patterns, recognizing, somebody whom I have seen in the past. If I see a picture of many faces, I will immediately be able to spot the face of a person whom I know, right? So these kind of pattern recognition tasks we are very good at doing. But Carver's hypothesis was not about the software algorithm part, but more about the hardware implementation substrate. So his point is, for algorithms like this, it makes sense to follow the hardware structure of the brain, which is use more of analog processing rather than traditional digital processing. Analog processing in the brain, for example, in the brain, we know there are computations that happen using analog quantities like voltages, currents, ion concentrations, and so on. Okay, so the postulate is, if you hopefully use analog computes in your circuit that implements the AI algorithm, then you can get these kind of energy efficiencies, which are like 10,000 times more power efficient than standard digital computers. Okay. So this is what I call is a neuromorphic version 1, which is talking about the circuits or the hardware substrate on which the AI is being implemented. But in the last 5 to 10 years, there has been a huge boom in AI, and a lot of people from different research communities have come in to develop AI hardware. And somebody from the computer architecture community, they will talk about any circuit that has a non-von Neumann architecture is necessarily neuromorphic, meaning memory and computation are mixed together. So it could be a digital circuit, need not be analog, but as long as memory and computation are mixed together, they would call it neuromorphic. Also, if you are using low precision in your computing, for example, instead of the standard 32-bit word in a digital computer, if you use, let's say, 8 bits, people would call that low precision computing also as neuromorphic. Now, if you go to the algorithms community, more like computer scientists, for them, they would call algorithms like spiking neural networks as a neuromorphic algorithm as opposed to using an artificial neural network. I'll introduce a little bit more about each of these terms later on in the later slides, but this is just kind of trying to set the context of what is the connotation of the word neuromorphic. And of course, the last part is if in your algorithm or in your network, the components are closely following the biological counterpart, of course, that is also called neuromorphic. So if you want to see how the popularity of the term has changed, this is a plot of Google Trends for the search term neuromorphic engineering. And this is showing you monthly search normalized to the maximum in this period from 2004 to 2020. And the maximum is normalized to 100. Okay. So what you can see is, there was a peak in interest in neuromorphic engineering around 2005, 2006, and it declined to a kind of a minima around 2010, right when I graduated from my PhD. Okay, so bad time to look for jobs if you are working in this area. But what you can see eventually is there has been a huge interest in neuromorphic engineering in the recent past, with a huge rise in this search term. Yeah. And you can get similar trends if you search using neuromorphic computing as well. You can just change the search terms a little bit. Alternatively, you can also look at some of our favorite nature series journals and search for the keyword neuromorphic, and again you'll see a similar trend that the number of papers with the word neuromorphic is kind of rising exponentially. Okay, so now explaining a little bit more details about the terms I used, the jargon I used in the earlier slide about computer architecture. What does it mean by non-von Neumann architecture? A typical computer that you are using today has what is called a von Neumann architecture, where there is a memory that is storing all the data and the instructions. And then there is a control unit that's reading the memory, performing the instruction, and writing the result back. Okay? So for every step, you need to read from memory and write back to memory. Okay? So memory access becomes a key bottleneck in some sense. So this is often called the von Neumann bottleneck. If you are doing algorithms and neural networks, where you have to read the values of the weights and the inputs and do computations, reading memory for every cycle, for every weight, becomes a tremendous bottleneck. So that's why people start thinking about non-von Neumann architectures, which is like what the brain does, which doesn't have a separate distinction between computation and memory. The cells or the neurons have memory and compute put together. Just like that, you can think about making artificial chips also that work in that way. So you can have neurons and synapses. Synapses are in some sense the memory. The neuron is in some sense the CPU or the compute. They can be put together in these units, and these units can be repeated throughout your chip. So you don't have a central memory or a central synapse bank. It's now distributed throughout your chip. So these kind of architectures are called non-von Neumann architectures or neuromorphic architectures. The other jargon that I used was in the algorithms part, something called a spiking neural network. What is that? So a lot of you are probably familiar with artificial neural networks that is very popular these days. So spike, you can think about a spike as a 1-bit representation of the output of the neuron. And that is very similar to what happens in biology. If you record from biological neurons, like the one that's shown here, the soma or the cell body is really the part where you think about looking at the output of the neuron, and it propagates along the axon and goes to other neurons. The inputs to this neuron or the soma comes from this part called dendrites, where other neurons are connecting to this particular neuron. So what you see, the inputs to these neurons are these impulses which just have a constant magnitude, right? So the magnitude of these inputs don't carry much information. It's just 1 bit. It's either present or not there. Okay, so these kind of inputs are called spike inputs, and their amplitude doesn't carry any value, but rather the time at which they are happening or the number of spikes in a certain time window is what carries information in this case. Again, you can take neurons like these and create larger networks like your ANNs. The only difference is all the communication between the neurons, all the outputs of neurons are like spikes like these. Other differences are, of course, there in the way you create the neuron itself. There is an integration of information happening here. So essentially, something that takes time variability of the inputs into account is happening in these neuron nodes, which is not present in your traditional artificial neural networks. So that's kind of the background. And if you want to look at some trends again about these 3 features of neuromorphic systems that I talked about, right? Which of these 3 features are really scientists looking at? Okay, so again, let's look at our favorite papers, in the Nature series or in the Science series of journals. And if you look at a Venn diagram of which aspects people are looking at, you see a huge number of papers are focusing on this spiking neural network aspect of neuromorphic, which is closer to biology. Okay, so in these nature or science kind of journals, people want to do something that's closer to biology, that's looking more at fundamental science. So you see SNN dominates, and people are generally looking at novel devices that can mimic biology. Now, if you come more towards the applied side in electrical engineering, where people are making neuromorphic chips or integrated circuits, and again, if you look at a similar Venn diagram, what you see is a large fraction of the chips that are being produced are actually digital. It's not analog. So really, in that case, what you see, the term neuromorphic is not used that much. People rather prefer to use the term non-von Neumann processors. So what you can see is, this area is very rich. A lot of different people from different communities are working, and they have their own definitions in some sense. Okay, so now with that background, let's now come a little bit towards technical content. So I'll talk about what are memristors, a term that some of you might have heard, and how we can think about building brains using memristors. Okay, so this is again showing you a picture of a typical artificial neural network where you have these nodes, which are neurons, and the connections between neurons are called synapses or weights. If I zoom into one of these nodes, it looks something like this. The inputs are x1 to xn. These weights are w1 to wn. Then what the neuron computes, it has a sum of xi wi, which is like a dot product between the input vector x and the weight vector w. That is added with a constant term b called a bias, and that goes through a function f, which is a nonlinear function, which is what the neuron is sort of implementing. So what happens in a standard ANN? Again, this is probably known to a lot of you, but because of the different backgrounds, I wanted to just cover this once. What happens in a standard ANN is these inputs change from sample to sample, and these weight values are learned through some kind of algorithm according to the task you want to solve. For example, if these X values are recordings from ECG, heartbeat, you could potentially train this neural network to see when a person is having normal heartbeat versus arrhythmia, some abnormal heartbeat, so that you can warn the person's doctor. Okay? So you can do some kind of classification task. So anyway, in a neural network, there fundamental operation that you are doing is a vector dot product with another vector. Okay. One thing that you can note over here is if you see the number of neurons, if they are order n, the number of synapses or the connections between neurons is order n squared, because you're connecting all the neurons in this layer with all the neurons in the second layer. Okay, so you can kind of see that implementing the synapse is kind of a bottleneck, a challenge. Okay, so this was ANNs, artificial neural networks. If we go more towards closer to biology, looking at what happens in the brain actually, then a neuron in the brain is more closer to what we call a spiking neuron. So in that case, what happens, the inputs to the neurons are generally slow input currents, and they're converted by the neuron into some precisely timed output pulse. Remember the 1-bit values that I was showing you? These are the output pulses from the neuron. Of course, if I want to implement them into a artificial brain, each of these circuits have to be compact and low power so that I can pack millions of them into one chip. There are some other requirements here, which I won't go into details, but essentially what you need to understand is a neuron is converting some analog input current into a digital, precisely timed output pulse. Okay. To make a network, I need to have the complementary kind of a structure that can take as input a pulse and create an output as a current. And that is done by the complementary block called a synapse in biology. So in biology, what happens? Input to the synapse is a fast digital pulse that converts this input into a slow output current. Now this output current can feed into another neuron, and you can now create bigger networks by alternating neurons and synapses. It's just like Lego. Again, there are several properties here. Some of the properties that are important is a synapse, when you make it in your circuit, it should have non-volatile weight storage, meaning if I'm learning something, for example, I'm a baby and I learned alphabets, I don't want to forget that, right? So the memory should not be volatile. Secondly, these memory values should be tunable, because when I'm learning something, I want to be able to change these weight values or the memory content. Lastly, something that I talked about a little bit, number of synapses is much more than number of neurons. So potentially, I would want these synapses to be much more compact and low power than the neuron circuits. So that one was more about what are the requirements of biologically motivated neural networks. Now we come to a different memory technology that has become very popular in the last 5-10 years as a potential device that can be used to make a biorealistic synapse. These are called memristors, and the term memristor is really an amalgamation of memory plus resistor. Okay, so essentially you see a number of devices here. You can see some devices like these. This is a voltage versus current curve, and you can see there is one state here where the current is very low, meaning the resistance is high. If you increase the voltage, it can switch to a different state where the current is very high, meaning resistance is low. Again, if you switch to a very negative voltage, this device can switch back to this high resistance state. So it has two states. You can have other devices like these ones, which are spintronic devices, or these ones, which have multiple states available as well. But in effect, all of these devices, no matter what the mechanism, from a circuit viewpoint, all of them are like resistors whose value can be tuned. What's the benefit of having resistors as a memory element? Think about it. Think about the artificial neural network algorithms that we thought about, a dot product between an input X and a weight W. See, if I make a crossbar like this with an array of rows and columns of resistors, if I give some input voltage here, the current output from the resistor is conductance times voltage, G times V. So you get a multiplication which is similar to W times X, right? So if the weight value I can store in the conductance of the resistor, I can directly do a multiplication within the memory. But what I wanted, if you remember, was sum over WIXI, right? That's the dot product. How do I get the sum? Well, the outputs of each of the resistors are currents. So if I just join them together, I can get summation of the currents through Kirchhoff's current law, just by a conservation law, right? So it's very effective in implementing neural network computations, these kind of resistive memories. There are other benefits as well. Because a resistor is kind of transposable, you can also give inputs from this side and get output from the other side. This is beneficial when you're doing learning inside this resistive network. Okay, but what you should really, the take home message is, if I have resistive memories, I can do a lot of computations within the memory itself, computations that are needed for neural networks. But this one was again ANN. What about SNN? It's actually the same thing. You can still use the same core circuit, just the inputs, instead of being analog voltages, they will now be these pulses with different times. And the outputs of these circuits can go into circuits that look like these spiking neural network-based neurons. Okay? These are called integer and fire circuits. It's a particular type of a neuron. We can also do other biorealistic learning mechanisms like spike time dependent plasticity, just by changing the shape of these voltages that are applied to the input and output of the crossbar. Okay? This shows you an example of different spike waveforms and corresponding learning curves that you can get just by changing these spike waveform shapes. As a reference, this plot shows you biologically measured data of learning from a actual synapse. Okay? And you see these kind of exponential decaying windows, which can be mimicked very nicely using these kind of resistive memory devices. Okay, so what we have been talking about so far is largely, the brain. So whenever we talk about neuromorphic, we first think about building the brain. But we have to take a step back and think, is really brain, does it equal to the entire nervous system? Actually not, right? Actually, the large fraction of our body is covered by what is called the peripheral nervous system, which is looking at nerves connecting all parts of your body back to the central nervous system, which comprises the brain and the spinal cord. What is the information that's flowing in this peripheral nervous system? If you think about it, most of the information is coming from skin, and skin has number of sensors. Typical sensors that are most popularly talked about are temperature sensors that help you feel whether a stimulus is very hot or very cold. And you have these kind of sensors which are in essence finding what's the pressure pattern that is being applied on your skin. Talk about two particular types of sensors, SA and FA. SA stands for slow adapting and FA stands for fast adapting. What's the difference between these two receptors? Very nicely shown here in the bottom. This plot shows you a force that's being applied to the skin. You can see there is some force being applied here. It's being maintained, and then the force is left. What you see here is slow adapting receptors are firing very rapidly when the force applied is very high and constant. What about the fast adapting ones? They don't fire very highly at that time. They fire more at a much faster rate when this force is actually changing. It's either changing up or going down, both these cases. Okay, so really the way you think about it is slow adaptive receptors are responding to the magnitude of the force, and fast adapting is responding to change in the force or derivative of the force. So that's how biology seems to have divided the sensing mechanisms. Why is it useful? For example, if you have very narrow pricks using a needle, these fast adapting receptors can still respond to that. But slow adapting are too slow to respond. They won't be able to respond to this. So, what we wanted to do in our work is to take a step back and think about the memristive technology. Can I use that to make these kind of peripheral nervous system building blocks? So now we come to our work, which is this memristive robotic nervous system. So we are trying to solve the problem of tactile sensing in robotics. And if you really think about AI, so I think the folks from computer science would really know about this more. You see a lot of papers talking about vision and audition, but very few papers talk about touch. But in our daily lives, touch is actually a very important sense. Where is it useful? Think about robotics. The things that even babies can do very easily, manipulate objects in their hand. Or think about it, in the dark you can put a key inside a lock and kind of twist it. That is very difficult for a current robot to do. So having human like tactile sensing is very useful. And of course the other obvious use case is in prosthetics, where somebody who has lost a limb, it is very important for us to give them back the sense of touch. So what is really holding us back? What is the challenge in creating a very large scale tactile array that is like the array of mechanoreceptors on human skin? Four major challenges that I list here. First one is latency. If I have a large number of tactile sensors, the way we read out the sensors is serially, one after the other. If you have too many sensors, it will take too long to read out. And then it will be very difficult for the robot to respond. For example, you have picked up a glass, and if it's slipping down, I need to immediately apply pressure and hold it. But if it takes too long, the latency is too much, I can't do that. Second problem is in wiring. If I have too many sensors, how do I wire all of them out to a central controller to read out? Third one that's more important in industrial settings is robustness or fault tolerance. If I somehow manage to create so many wires that connect back to the controller, what happens if one of those wires is cut or damaged? It's like, think about it. If you have your computer and I damage one of the wires, the whole system starts to malfunction. It's not very fault tolerant. The last thing that a lot of people don't talk about is the feeling of pain. Mostly when people talk about tactile sensing, they want to create sensors that are very sensitive to pressure. But think about how we as humans have grown up. Pain is one of the most important teaching signals that are available to us that tell us how we can respond, right? I don't want to touch a hard object very hard. Don't want to hit it hard because I know I'll feel bad. But a robot who doesn't feel pain will not know that. They might actually damage their hand by really, banging into a metal plate. So these kind of things that seem common sense to us are coming because of teaching signals that are available. And these are the things that we want to give to our next generation of robots. So what we came up with was a memristive robotic nervous system, and that has robustness and scalability due to three mechanisms. The first one is a pain receptor that we made. So in some sense, if we can give the robot a sensor that tells them what is pain, by virtue of a reflex arc, the robot can now take their arm away from a painful stimulus and therefore avoid damage. Okay, this is showing you example of a pain receptor response. And really what a pain receptor does is, if the pressure or the temperature coming from the sensor exceeds the threshold, it sends a series of pulses back to the brain that says this stimulus is harmful. Other important things that happens is, after an injury, the pain receptor actually has a reduced threshold in some sense, so that the next time somebody tries to injure that same portion, it will have a quicker response. And that's what you kind of see here. Right after the response, the output of this pain receptor is very high, and slowly with time, 5 minutes, 10 minutes, 15 minutes, it slowly relaxes back to the baseline. This enables, this sliding threshold kind of mechanisms enables the pain receptor to tell the robot that this part has been damaged. Quickly remove it if you're again seeing harmful stimuli. Second part of robustness comes from this self-healing aspect, which was really a wonderful piece of work done by our colleagues in the material science department. By the way, I should strongly emphasize that this work was done in conjunction between electrical and mechanical science, so it wouldn't have been possible at all without this kind of interdisciplinary collaboration with the group of Professor Nirpan Matthews. They came up with this wonderful self-healing mechanism of the sensors, where you can see that, before damage, this is the sensor. If there is a cut here and these two things are damaged, they put a ion gel on top of these sensors, such that even at room temperature, the ion gel can coax these two parts to sort of stitch back together. Okay, it's like our actual skin that also stitches back together over time. So you can see this signal coming out of the skin normally. This is signal after damage. There's no signal basically. And again, after joining back, the same signal can be measured again. So this is good. We have healing like the skin. We have pain like the skin. What else? The third problem, biggest problem, in fact, is wiring. I was telling you earlier that if I have a large array of tactile sensors, how can I wire each of them out to a central processor? That becomes a problem. How does biology solve it? Biology actually does wire out each of the sensor to the central nervous system. They can do it because they have three-dimensional wiring. In our artificial systems at the moment, we only have two-dimensional wiring on the surface of the skin. So with this kind of two-dimensional wiring, it's impossible for us to replicate biology. So what do? We thought about doing something that's very different. Instead of having intelligence separated into the central nervous system and sensing in the peripheral nervous system, we fused them together and put intelligence in the form of synapses and neurons into the skin that we developed. Okay, so you can see here this kind of a cartoon that's showing these inputs are coming from the pain receptors. These inputs are coming from the tactile sensors. So what we are doing is we are performing associative learning on the skin. If there is some harmful stimulus like a sharp object, then these pressure patterns are coming from the tactile sensors, and these red patterns are coming from the pain receptors. So what you can see is this pain receptor is sort of a teacher signal that's teaching this neuron that when it should fire, whenever it sees a painful or a noxious stimuli. So you can see every time the red stimulus is there, this neuron is firing, and over time what happens is the weight values connecting to these particular inputs also are learning that these are the painful stimulus. So you can see these weight values are increasing over time because they're learning that this particular pattern 1010 is the painful pressure sensor. What happens because of that? After learning, even if the pain sensor is damaged, in this next panel you can see the red pain sensor outputs are no longer there. But because this system has already learned what is a harmful stimuli, even without the pain sensor, it can now cross the threshold and fire a spike every time there is a 1010 stimulus, which is the painful stimulus. So essentially, due to learning now, I have increased fault tolerance and I have reduced wires, because these wires only need to go to this neuron, which is right there on the skin, not on some external processor. Okay, so I should emphasize this is different from biology. In some sense, what we have done is we have merged central nervous system into the peripheral nervous system. So that's why we don't call it PNS in our paper. We call it a robotic nervous system, which is kind of different from biology. Okay, so this is, I think, a video that shows you how the robot learns to recognize pain and learn damaging stimuli. So the video is kind of, self-explanatory. You can kind of see. Before training, the robot is not going to respond to pain or damage. And this wire connection is being removed. And this pressure sensor is being pinched to represent the pain signal. And the robot does not move its arm away. So now we connect the robot back, pinch the pressure sensor 3 times, and the robot understands its painful stimulus, so it moves the arm away. Okay. And we keep on doing this number of times to teach the robot. This is where learning is happening in the synapses and the neurons. Just like you're teaching a baby, you have to actually do this a number of times to teach the robot. But now what happens is the wire connection is again removed, meaning the pain sensor is damaged. But now, after training, when you pinch the robot, the hand can actually move away because the robot now remembers this was a harmful stimuli. Okay, so that's most of the details of the technical part. I want to finish the talk with some conclusion and future directions where I think neuromorphics can be very useful. First part is obviously an extension of this work. What we have done so far is just very rudimentary building blocks. We still haven't gone and connected this with a central brain and used feedback to close the loop and change an actuator, for example, an actual arm or a hand that changes based on these sensors. So we are planning a big project with several components where, for example, we have these artificial neural networks that are similar to the skin, which is what I presented. And these outputs have to be processed by a central computer. And based on this, we will plan to use something like a reinforcement learning scenario to teach this artificial brain how to work with these new kind of skins, and eventually then transfer this to real life scenario where this can be used either on a robot or on a prosthetic hand. Second place where this is very useful is another part of the work that we do is brain-machine interfaces, where we think about implanting probes like this into the brain of a patient. And these patients typically are tetraplegics who cannot move their arms or legs. So for them, having some way to communicate with the world or to do their task by themselves is a big change in lifestyle. Okay? So we use these probes to record signals from their brain, and we use those signals to change, for example, move a wheelchair or move a cursor. But moving a wheelchair or a cursor is much easier than actually moving an arm, because in an arm, you need to know how much pressure you're applying. For example, if you're lifting a paper cup versus lifting, let's say, a steel cup, you need to have different types of pressure. Okay? So for that, you need to give sensations back to the user through a mechanism called sensory feedback. And that's what we can do with this kind of artificial skin. We can actually give sensations back to the brain and form a closed loop that should enable these kind of paraplegic patients to now use artificial limbs. And the last one is probably a little bit futuristic. I think we can do something like ambient intelligence using these kind of devices, because the technology that we are using is more like printed electronics, which can cover a large area. You can actually now think about making, covering walls of big buildings using these kind of materials. And these can be something like a cognitive sensing surface. Okay? These can actually sense when humans are close by, for example, or they can be paired with CMOS chips, and together they can actually give you more intelligence than what we can get using, for example, cameras that we have currently. Advantage, the neuromorphic approach, the advantage that it gives is these memristive sensors can already do a little bit of filtering. you think about it, if I am spreading the sensors throughout the walls of a building, we have millions of sensors. Having to scan them is impossible. Again, the neuromorphic approach where each sensor actually sends out these spikes or 1-bit values is important, because then I don't need to scan out. Only places that have information will automatically send information to me. Okay? So this way I can actually scale the system to cover buildings and have what is called ambient intelligence. And this thing is probably most important in healthcare. I am showing you the picture of a recent review paper in Nature a few months back that's talking about how ambient intelligence can help you in changing healthcare and really keeping track of what the patients are doing even at their home. So I think with that, I'll stop my talk and I'll conclude by saying that Neuromorphic has a lot of opportunities across the stack, from circuits, architecture, and algorithms. And at this point, I would thank all of you once again, and I'll be happy to take any questions. Thank you very much.
Thank you, Prof, for that insightful glimpse into the future. Before we move on to the Q&A session from the audience, we have Anup from the MA Graduate Students Club, Shingchi from the MSc Graduate Students Club, and I would like to ask you a few questions about this topic. So first up, we have Anup. Anup, over to you.
Can you listen to me?
Yes, I can hear you.
Yeah. Okay. So, Prof, a human skin is gold standard for artificial skin, and it's multifunctional. It can sense a hot, cold, smooth, rough, pressure, tickle, itch, pain, vibrations, etc. Every now and then we come across research on artificial skin which aims to sense a subset of these sensations, but not all of it. Also, the appearance doesn't look like the human skin. How far are we to matching all these incredible sensing features of human skin simultaneously, as well as replicating it in appearance? Also, when can we expect really to see a full-scale human-sized humanoid with artificial skill like humans working collaboratively with humans?
Okay, thanks, Anup. There's a lot of mini questions there. Maybe I try to dissect and answer them one by one.
Okay.
Firstly, in talking about the number of different sensing modalities,
Yeah.
broadly speaking, I think temperature and pressure would be two major modalities, and the other parts that you talked about, uh, pain, for example, is something that we showed. You
Yeah.
can do that by putting some thresholds on the normal pressure sensor, on the normal temperature sensor, which is now possible. We are showing that we can do that. The other parts, like tickle sensation or very faint kind of touch, all of those things I feel would be possible if you had higher higher temporal resolution of your tactile sensor array. So I think that is possible based on the neuromorphic approach, where we are having each sensor kind of send out its own output without waiting for a scan to read all the sensor values. So the latency part can actually now go away. So I think with the latency part going away, if you have sub millisecond kind of latency and a large array of tactile sensors, uh, I think all of these features of human skin are possible. But what's difficult is scaling it down to the same size scale that we have in human skin. But I think if the electronics part, wiring part, all of that is taken care of, I think in material science, people are already making these memristors very small in the micrometer scale so that they can go up on top of integrated circuits. I think that same technology can be borrowed and ported over to human skin or artificial skin. So I think it's possible. Uh, in terms of when, I really think some artificial skin on a humanoid robot will be there, working with humans. I am I'm quite hopeful that maybe in the next 10 years we'll probably start to see something where in factories we can have humanoid like robots with artificial skin working together with humans.
Thank you, Prof. Thank you very much. So that's my question only.
Okay, thanks. Anup.
Next, we have Shingchi from the MSc GSE.
Okay, hello, Prof.
Hi, Shinchi.
Very nice talk, and I have several few questions. That where did you get the idea of distributing mini brains throughout the lower skin? And it can reduce the connecting wires, but also requires more processors. So how did you balance the skin and the processors? And also, what kind of feature do you think is important for the materials used at the lower skin?
Okay. Uh, so the first part of your question was about how did we think about putting the mini brains in the skin. Really, this inspiration comes more from in electrical engineering. Some of you would have heard about the term Internet of Things. Basically, we are talking about bunch of sensors distributed throughout a building or a city that's capturing data and sending data back to the cloud. So
Yes.
in that case, we often think about pushing intelligence to the sensor in what is called edge computing. Instead of sending data to the cloud, we actually have the AI in the sensor itself.
Mhm.
So now when we think about the skin problem, it kind of struck us that this is kind of a similar issue. Most people are just having a big sensor array on the skin and then reading it back out to a central processor. So can we get inspiration from the Internet of Things, IoT, and try to distribute the intelligence within the skin array itself? That's Does that answer your question?
Yeah, yes, okay.
I think you had a second question about what materials
Yeah, yes, yes.
are useful. In terms of materials, I think the way we are approaching is definitely we want to have the materials to be flexible so that you can cover or conform to different shapes of robots. Secondly, we want them hopefully to be printed material so that you can make it very cheaply, because when you have robots working in some rough environment, it's easy to damage. So I should be able to print another skin and put it back. And thirdly, what I was really intrigued by was what our colleagues in material science did in this self-healing aspect. So I think if you can do that, then the robots, the electronics part will become so much more robust. Even if you have mechanical damage, you know that after some time it's going to heal, it's going to start working again. So I think these three properties are probably the most important ones that I see.
Okay, okay. Thank you, Prophet.
Thank you, Anup and Shingchi. Now, I would like to ask you a few questions from Tripoli side. So you talked about the mini brains, and I wanted to know if there is any coordination control between these mini brains, these processors, and the central brain in the robot, and if so, how is it implemented?
Okay, so that's a very good question and a tough one. So what's happening currently is these mini brains, you can think of them as sort of filters that's filtering out what information goes upstream to the central brain. Okay. So in some sense, it's not allowing all of the information to go to the central brain so that the central brain is not overwhelmed. In terms of coordination, therefore, it's like unidirectional. It's not really bidirectional. But how do we have bidirectional can be indirectly. Right now, we have not done any closed loop tasks. Closed loop tasks means, for example, again, if I'm lifting this object, the pressure sensors on my hand are telling me what is the weight of the object. Based on that, I know how much pressure to apply here to not let it slip down, right? So it's really closed loop. I'm sensing the pressure, then applying a force to keep the object in place. So the moment we start doing these closed loop kind of things, potentially there will be need of coordination between these mini brains and the central brain, because the mini brain, for example, can take a quick decision and avoid the slipping of the object by quickly changing the force, whereas the central brain can probably take more time and assimilate information from many mini brains and then take a better idea about what's the perfect force to be applied for this particular object and so on. But we have not implemented that yet. That's kind of future work.
Right. And you did talk about how the future scope of neuromorphic AI looks like. So my next question to you would be, for us students right now, what are some of the subjects or the topics in your opinion that we should be focusing on if we want to contribute to this field?
Okay, so as I said, this area is quite broad, so you can attack it from many angles. You can come from material sides and make unique devices. You can come from the circuit side and make circuits that behave like this, or you can come from the AI side and algorithms and think about, how do I deal with these 1-bit representation of signals. So it's all of these are possible. So what I would probably say is, because it's interdisciplinary, it's very easy to get lost. I think at an undergraduate level, it makes more sense to focus on one of these areas and be more of an expert in this, so that later on you can actually talk with folks in other areas, actually collaborate with them, and probably build up on larger interdisciplinary projects. That would be probably my advice.
Okay, thank you, Prof. Now we'll move on to the Q&A session from the audience. We already had a few questions that were asked to us by the registrants before, so we'll start off with those. In the meanwhile, everyone can put their questions in the Q&A section, and after these questions are answered, we'll take those on. So the first question comes from Kai Jiangqi, and he asks, where do you get the idea to design the neuromorphic AI? Is it modeling the actual brain neural network, or is it functioning similarly as the neural network but not exactly modeling it?
Okay, so that's a very good question. I would say historically, when this whole field started, we were really trying to do more low level modeling of ion channels in the brain, so very close to how the brain works. But the problem in that approach is we still don't know a lot about, what the brain actually does or how it does it. So though we could very nicely mimic subparts of the brain, we could not really get to an abstraction level where we could see real function coming out. So now we have taken a step back, and what we are doing is more, we are taking inspiration from what we know about how the brain works, and we are trying to make something that's like the brain but not exactly mimicking the brain. Does that answer the question?
Right. You actually answered part of the next question as well, from Burak Satar, and they asked, is it really possible to emulate the human brain while lots of the secrets of the brain are unknown? And another question from them is, will these mini brains be able to help robots to act like and feel like humans?
Okay, so yeah, indeed, I think part of the question is overlapping. So indeed, we acknowledge that we don't know a whole lot about how brains are working and how they are giving rise to behavior. But so that's why what we are doing right now is we are trying to go with what we have, with the parts that we know, and try to take inspiration from that and modify traditional AI algorithms, traditional AI hardware, with some inspiration from what we know that happens in biology. In terms of whether it will modify how robots feel and act, the feel part, yes, we can say that it's very similar to the pain receptors in biology. So the robot would be feeling something similar, but whether the behavior will be similar or not, as I showed you, what we are doing right now is very simple reflex action, right? But in humans, there's potentially a lot of other things that happens, right? If you are burned by a flame, there's probably a big part of your memory that gets modified, and that you really understand this as being a very harmful stimulus, and you can potentially project to other cases where you see something that looks like a flame and you start being afraid. So a lot of those things we don't yet know how humans do. So that part probably won't happen right now in robots either.
Thank you. And the next question comes from Lin Mintu, and their question is, what's the main bottleneck to further progress in this area? Is it the robotic side or the neural network side?
Okay, so I assume here that by the robotics side, Lin is talking about the hardware part. and the AI side, really, he's talking about the algorithms, the software part. So I would say really the bottleneck here is probably on the more on the hardware side, because uh, the AI guys or the algorithm guys will tell us that, okay, you haven't even given us what a actual realistic human touch signal looks like. What does that high dimensional signal look like? If you don't give that to me, how will I know if my algorithm works or not? So fair enough. So really, I would think at this point the hardware part of creating the tactile skin array is what is missing. So once we have robust hardware and we can create a lot of data sets, I think at that point the ball will move to the court of the AI algorithms folks to see if they can use this and create, sensory motor behavior like what we see in humans.
Okay, the next question comes from Ong Lee Han, and their question is a little abstract and aligns with your future scope of your work. And the question is, what are your thoughts on Neuralink and the technical or perhaps the ethical challenges that it will face?
Oh wow, this is a good question, and a question that could be talked about for an hour. Uh, Neuralink is actually doing something related to brain-machine interfaces. I kind of had one slide on that, and currently, what Neuralink is doing is they are showing they can read data from the brain and also stimulate parts of the brain, which is in some sense writing data back to the brain. Um, the technology that they have shown so far is known to us for a long time. What they have done very well is in terms of really going over the engineering hurdles and solving them, really implementing it. Technical side, I mean, so really it's not that related to what we are doing at the moment, because we are doing more like peripheral part. Where it can be linked is if we use this peripheral part sensing and then write back these signals into the brain for sensory feedback. That's a technical part. The ethical part is actually kind of very difficult to say. Is this technology useful? Brain machine interface. Definitely, if you talk with any of these patients who are paralyzed, or talk with their family relatives, I mean, this kind of technology is giving them a shot at being independent at their own life, just going about their activities of daily living themselves. That is a big thing to them. So definitely the technology is needed, it's useful. Can the technology be misused? Unfortunately, yes, it can. So just like any other technology, like nuclear technology, you can do good, you can also do bad with it. Potentially stuff where it can go wrong. Of course, one place where it can go wrong is hacking, right? If you're giving some hackers a chance to read your brain thoughts, that's dangerous. That's your most private thoughts, and you're letting somebody else read it. So that's very difficult. Of course, you don't want to do that, right? So security, hardware security is one aspect, but another aspect that's probably more disturbing is, people talk about these kind of things that, if I can write data into the brain, um, think about the current judicial system. If there's a criminal who has done something wrong, we punish them by different means like imprisonment for several years, and the hope is the person will rectify their behavior, right? And so potentially, what if you could actually write some data into their brain that explains to them what they did was wrong? So that seems great from a government viewpoint, maybe great, but really, do we have the right to alter their brain or alter their perception? That's actually very difficult to say. I think we don't. Um, that being said, probably this technology is going to be developed, and you're going to see more and more of this in future. It's very important to keep these questions about ethics alive. So at least there's a voice that's protesting against these kind of things. So the corporations at least know that there are people who understand the problems with this, and you can't do whatever you want. So yeah, so it's a kind of a long-winded answer, but I guess there's no clear-cut answer. The ethics part of this kind of research is always a bit of a gray
So
area.
yeah, so it's an exciting field, but clearly we need to proceed with a little caution eventually.
Yeah.
And the last question that came from the registrants before is a more realistic question, and it comes from Bamsi, who asks, are there any potential possible final year project opportunities in this field, or are there any part-time roles or internships?
Final year projects, there's a ton of them being offered. I think both from my side, from Nipan's side in material science. For folks in mechanical and aerospace, you can look up Professor Domenico Campolo. He does a lot of work in this area, and we are all collaborating, all three of us. So yes, we can potentially definitely float projects according to what you want in this area.
So I think a lot of professors, including you, are going to receive a lot of requests after this talk.
Okay.
Moving on to the questions from the audience, we have about 10 questions. So the first question comes from Christopher Luanga, who asks, for slide 27, how many samples did you need to train the robot to recognize pain? That's the first question. And the second question is there a digital computer involved at all in this training?
Okay. For this particular slide, you can kind of see, let me see if I can go back to, you can sort of see over here, it takes about, in this case, 3 samples. But in general, if I repeat it across many different samples of these synapses and neurons, somewhere between 3 to 10 number of repeats of trials are needed in general. Digital computer being needed in this whole loop, yes, if you see the actual setup, what's happening is these pulses that are being applied are actually being applied through a Arduino board. So in some sense, though the internal computation that's happening is in analog, we are using an Arduino to communicate and log the data in a computer.
Okay. The next question comes from Sharat Kumar, and he asks, would AI accelerators that are present in the newer processors qualify as digital non-von Neumann architecture chips? I'm curious about the interest in this topic from the digital IC design perspective.
The AI accelerators that are present today. So in the AI, for example, in the digital IC research area, definitely a lot of people are making these processing element based arrays, where each processing element has a bunch of memory and bunch of computation put together. So this is indeed a distributed memory approach and would be a non-von Neumann approach. In terms of products, I don't know products that I would really say are neuromorphic. For example, I know there are Intel has a chip called a Loihi chip that is in this format, but it's not a product yet. IBM has a chip called a True North chip, which is again a non-von Neumann processor like this, but it's also not really a product yet. But I think spiking neural network chips from these big companies, though haven't been productized, I think general digital processors that are more like non-von Neumann, there are many startup companies that I know that have come up with products of this sort. So yeah, indeed, there are digital ICs, digital accelerators, which would fall in this non-von Neumann category.
All right. The next question is again from Christopher, who asked, for slide 9, does it mean the biological sensory neurons do not encode information in the magnitude of the spike, or do you mean for purposes of developing neuromorphic computing platforms, you deliberately choose to only encode information in the temporal spike pattern?
No, actually, in biology, that's the current understanding, that the magnitude of the spike doesn't encode information, even in biology, not only in our implementations.
All right. The next question is from Wangbo. He says, thanks for your presentation. I'm Wangbo from SUTD. Can I know what algorithm for training is adopted in the robotic? Do you think STDP will outperform conversion of pre-trained ANN in SNN training? And for neuromorphic IC, what do you think synchronous design versus asynchronous design? Which is the more prominent future?
Okay, so several things here. In the work that I showed here, there was no big, large level neural networks. The only one that was shown was these mini brains. These mini brains are using something like STDP to learn associations, because we are only doing associative learning here. In terms of larger, deeper networks, it is kind of now a consensus that STDP alone is not able to produce as good results as converting pre-trained deep networks to spiking neural networks. So that is true. However, there are some evidence that, when you are training the networks directly using backpropagation in the spike domain, initializing the weights after STP learning might have some value. So you can probably train a little bit faster. The last part, in terms of digital chips, whether synchronous or asynchronous, which one is going to work better? Currently, the issue is asynchronous design, though from a theoretical viewpoint, that is really ideal and should be the way to go. There are no EDA or design automation tools that are publicly available for us to use and design asynchronous chips. Okay? So that, I think, is the biggest bottleneck, and that's why I think what will happen largely that I see in the near future is people doing more like synchronous designs, but that are kind of woken up asynchronously, and only when there is a stimulus, the chip wakes up and does something. So an asynchronous wake up followed by a synchronous operation is probably more likely. That's what I feel.
Okay, so the next question comes from Mehdi, who asks, thanks for the great presentation. How did you give feedback to the robot regarding pain? After touching the pressure sensor for 3 times, did you give feedback that it is a pain? And why 3? Does it get sensitive to the pain strength of only touching the arm 3 times? How long did it take for you to train it?
Okay, so 3 is just an arbitrary number. Anything larger than 3 will also work. So essentially, the pain part is really putting a threshold on the pressure input in some sense. So if the pressure input is stronger than a certain amount and is there for a duration that's long enough, then the robot starts feeling pain. So 3 is just an arbitrary number, arbitrary threshold. You can make it higher, make it lower. It's up to us. In terms of feedback, yes. So what's happening is, if you let me see if I can go to that slide again. See, what's happening is the pain signal. So these inputs are coming directly from the pressure sensors. These are going to the robot. Along with that, the feedback that's really going to the robot is this part, which is really coming from the pain receptor that tells the robot whether this stimulus is painful or not. So if this feedback comes to the robot, only then it starts to learn this association of this particular stimulus with this feeling of pain. Okay, and this is what it shows, that after the association is done, even if this pain stimulus is not there, whenever this pattern 1010, which we are calling as the painful pattern, whenever this pattern comes, the robot is still going to respond with a output that says, okay, this stimulus is bad.
Thank you. The next question comes from John. He asks, I think this would be very fascinating for VR or AR. Any thoughts on combining this with neuromodulation, similar to Stephen Potter's work from the 90s?
Wow, somebody remembers Steve Potter's work. Steve Potter essentially was at Georgia Tech, so that's where I graduated, so I know Steve very well. We haven't thought about neuromodulation, to be frank, but what we have thought about is AR VR, because we can potentially have these latency of the touch signal to be very short, because we are using this spike-based approach that allows very quick readout. It would be very nice to give haptic kind of feedback in AR VR situations. So that definitely is one of the big use cases that I think might be a commercially more viable case, because the prosthetic one is more closer to my heart, but the market size is not as big. So taking it to market, probably AR VR is going to be one of the biggest drivers, I think.
Thank you. John, if you're here, I saw your second question, and it mentions the term closed loop neuromodulation, and I believe Professor kind of answered that as well. So skipping that, which is the same question, the next question comes from Sharath, who asks, I would also like to know some more about the energy requirements for the sensor array. Is it a passive system? Further, if it requires a source of power, how would we provide this in biomedical applications such as implants?
Okay, so few parts there. First part is it's not passive, because for each pressure sensor we are keeping this oscillator like structure that creates these pulses. So those oscillators require a power supply, and currently the power supply is coming through a wire connected to a battery. Okay. For an implant case, think about it, this skin is actually not going to be implanted, right? It's going to be covering artificial arm, so it's just outside, and you could potentially just have wires going to that. But it's an interesting question. There is a potential, and some of the work we are doing currently with Nirpan's group also does it. These devices that we are making can be made out of solar cell material. So potentially, you could actually have a skin that is sort of can harvest energy from light. So if that is possible, in that case, you could potentially even have self-powered skin, because the energy that's being harvested could be used to power up these oscillators themselves. But we haven't done it yet.
Yeah, but that's a very fascinating thought. That next question is from Cooley Han. They ask, I've heard of dual AI systems, central and the dedicated AI, in other applications. I know this isn't exactly specific to the topic at hand, but why would you separate the central and the dedicated system instead of making one neural network that can be used for multiple applications of such a neuromorphic system?
Okay, I I'm not sure I understood the question fully, but maybe I can explain it this way, that in terms of a network architecture, you can still think of the whole system as inputs coming in and then going to a big neural network that's being trained directly. That's fine from a mental viewpoint of picturing the network. But what we are doing here really is we are saying, in terms of implementation, you should implement part of the network right at the skin itself, because if you do that, then lot of the information doesn't have to be wired back to the rest of the bigger brain. Why? Because wiring these things back to the brain is a challenge. That's really why we don't want to wire. For example, if there are 1 million skin cells, tactile sensors, connecting all of them back to your central brain would require 1 million wires. That's very difficult to do. But if I have a first layer of neurons on the skin, which reduces this 1 million wires to 1,000 wires at the output of the neurons, wiring these 1,000 wires to the brain is a lot easier. Yeah. So it's really a practical case of hardware issue. Like, how do you really build it? That's the motivation for us to separate out the neurons, part of the neurons in the network, out into the skin, versus keeping all of them into one central area.
And the last question comes from Kikai Jiang, and they ask, a fascinating thing biological neurons can do is that they can modify themselves in terms of neural morphology or synapse connection. And one way they do this is by gene expression. Do you think that there is a way to implement this idea into the neuromorphic devices?
Okay. This is a very nice question. Indeed, in biological neurons, there are neurons with different morphologies, and I showed a little bit over there that the dendritics tree, the part that captures data from other neurons, it's actually very different for neurons in different parts of even pyramidal neurons in cortex. That's very different. Uh, Changing them on the fly within this kind of a hardware neural network is very difficult. Frankly, I personally don't know how we could do that. Potentially, I don't know if you have a bunch of silicon nanowire kind of structures, and maybe you can use heat to kind of rearrange them or something. Uh, we haven't really thought about that. What we have done is, in chips that implement these kind of neural networks, there we can actually program or program on the fly connections between inputs and dendrites and change the length of dendrites and so on. So we can do electronic programmability in a much easier way in silicon chips, CMOS chips. But doing them in this kind of printed flexible hardware is a very intriguing question. I have to say we don't know what to do about that. I'll have to think about it.
Professor, there are two more people who wanted to ask questions. Would you like to take them up
Sure,
right
sure,
now?
sure, sure.
So the next question comes from Vivek Mohan, and he says, "Thanks for the great talk, Professor. I have two questions related to the tactile sensing part. The first is the learning mechanism for the e-skin pain sensing similar to some kind of associative memory, like bidirectional associative memory? Is implementation in the form of resistive memory network uh, as well?" And the second question is the e-skin sensor of FA or SA type?
Okay, good questions, Vivek, both of them. So first one is uh, the first one was, I think, the pain sensor. The pain sensor itself is not an associative learning mechanism. The pain sensor, this nociceptor or the pain receptor, is this diffusive memristor, and that is really creating a threshold on the original pain signal and creating these pulses. The associative memory comes after the pain receptor, where we have these synapses and the neurons. Along with the output of the pain receptor, this part is where it creates an associative memory. And it is, yeah, indeed, somewhat like these bidirectional associative memories in some sense. Uh, though I wouldn't say it's bidirectional because I really can't recall this particular pattern. It can only recognize that this pattern was in the memory. Second part was about SA or FA. These the ones that we have currently is the neuron is really just taking the raw magnitude of the pressure sensor, converting it into pulse outputs. It's not differentiating the raw pressure, so it's more like a slow adaptive pressure sensor. It's like a SA type of receptor.
And the final question comes from Vinay, who asked, for someone who has just been introduced to this field, what resources would you suggest to look at?
Okay, so this again depends on your interest, because if you're looking at neuromorphic circuits, there would be a bunch of review papers or a couple of books that you can look at. If you're looking at spiking neural network algorithms, then again you can look at a few books. For example, the ones by Wolfram Gerstner, which is available online freely, is a very nice resource to start from. If you're looking at memristive devices, again, more from the device viewpoint, again, you have to look at corresponding reviews in journals like, for example, Nature Nanotech or Nature Materials and so on, which would give you an idea about what's going on in this area. So because again, this area is very broad, you need to focus a little bit on your particular interest area, and you can look at, there are a number of good review papers out there, so which you can start off from.
Well, that is it from the audience Q&A. Thank you once again, Professor Basu, for taking time from your busy schedule and joining us for today's webinar. And I would like to thank all of you who joined in for your wonderful participation in this event. Now, before you leave the webinar, do scan the QR code which will appear on your screen in a few moments for the survey and the attendance form as well. And we value your feedback to help us improve future webinars. That's all from my side. Please hold on as the QR code slide is shared on screen.
Thank you very much, Shantanu, for hosting the event. It was very welcome.
Thank you. So I hope everyone can see the QR code on their screens now. Please do scan it and fill it.
Thank you, Prof. Basu.
Thanks, Chris. So I guess I'll be leaving now.
Okay, thank you.
Okay, thanks a lot.
Thank you, Prof.
Bye.